Hello, everyone. Today I will register part of my study. The I will continue what I was studying the last video, which was the role of the flash temperature in rubber friction from BNG person. Okay, let's continue. But previously, my name is Anderson. I'm a mechanical engineer, Brazilian one. Um, Graduated in Brazil, but with a master degree in the uh, Modena University in advanced automotive engineering, and now I'm in the Brescia University developing a PhD in rubber friction. So let's start. Let's check something. Okay, in the last video we stopped in the macroaspherent contact area. So the next part is, uh, Pearson defined the friction, but in the part that it relates the load and contact area, nominal one, he normally uses some contact mechanic theories derived from Ashard, from Greenwood, in order to find a correlation between normal load and nominal contact area. Because in rubbers um, this proportionality is not direct. Actually, is quite nonlinear. So, and this is important to have a correct prediction of the rubber friction. So together with the surface roughness, we need a good proportionality function between the normal load and nominal contact area, which is Pearson is doing here. Now, consider the contact between two solids of at no low. Let me um, put this video in this article in the screen. I think should be a good one. No. That's I will explain. So the author considered two solids in contact at low nominal pressure. So sigma zero equals Fn over A0, which is the nominal pressure, where the contact is proportional to the load. It is a condition, very strict condition, in which the load is not too high, is not high enough for the correlation between load and area became no for the correlation between load and contact area become nonlinear. So in this case, we can assume some linearity. So consider first the system on the length scale lambda 0 for this nominal condition over zeta m, which is the magnification m. On this length scale, the solids will make apparent contact at low concentration of contact areas. And and this is quite nice because I will put here an image. Bibliography, rubber. Oh no. rubber piece. Okay, 2000 and what? 2006-1. I will try to leave this image to you. Okay, pay attention in this figure. So, on this length scale, the solids will make contact at low concentration of widely spread contact areas. Okay, and I will explain later this picture. Since the separation between the microsperity contact regions is very large, we can neglect the interaction between the macro regions. In this case, the pressure in the microsperity contact regions will be out of order. In the word out of order of magnitude of Q0 times H0, our height, and the elastic modulus, this product, where H0 is the RMS, roughness amplitude, and E is the elastic modulus. Okay. Let me. So let's go to this part here. We are here. Here. Thus, the average pressure in the microsperity contact regions is independent of the nominal contact pressure sigma 0, which is Fn divided by A0. Now, each microasperities is covered by a smaller microasperities, and the smaller microasperities is covered by even smaller asperities, and so on. It is easy to see. I will leave you with this picture here. It is easy to watch, to observe that the microsperity contact regions will be very closely separated. It is therefore impossible to neglect the elastic thermal interaction between the asperities and at short enough length scale. So, what is the point here? I believe I discussed this in the last video, which is we increase the magnification. We see more and more roughness. We see more and more micro roughness in a macro roughness. And these micro roughness are close enough to the other asperities such that when in contact with the rubber, each asperities will interact with the effects of the other asperities and so on. So when you need the flash temperature, okay. Let's, here it is, figure 5. This is a very interesting point because here we see this uh, effect from Pearson, because you see a tire with very clear contact zones, but with an infrared camera, we can see that we should see everything, every contact zone red or yellow, depending of this how is the color scale of this camera. And the problem is neither uh, all the contact scale is red, which means that the rubber is not totally in contact with the rubber, but also we have points, very local sections, very local points in which the temperature is the highest one. You can see it by small yellow points. I will increase the zoom. You can see this from here. You can easily observe this. And this is the point. This is the very important point here. Here is the effect of magnification when observing the contact area. So we have a magnification, let me check. On the left, zeta equal 4, and then on the other side, zeta equal 2016. So these are the effects of the magnification, but not only, we are really seeing the real contact area. Okay, I think we can discuss the part of temperature, I believe. Let me check. Okay, we can discuss this part. Okay. Let's remove the zoom. Okay, I think I return to my screen. Okay, so as you see it, yeah, it is important to point this previously to analyze the flash temperature. Okay, rubber friction without flash temperature. Now, Pearson will consider the effects without the temperature. Let's check. And I believe I already discussed this in my text, but let's see it. Mm, Okay, let's talk about this. So, rubber friction without flash temperature, we are just considering when I have a block sliding on a rough substrate or a tire over a road. Okay, the oscillations caused by the asperities triggers viscoelastic effects on the rubber, which causes a viscoelastic energy dissipation. The author already developed in the date of this article, a theory which describes this energy dissipation process and which predicts the velocity dependence of the rubber friction coefficient, which I already wrote in my notes. Actually, in what is the point? The friction coefficient depends on the viscoelastic modulus. So that is a function of the viscoelastic modulus and is the viscoelastic modulus in function of the frequency. The power spectral density, okay, and this is it. Why? Because when we are not considering heating effects, we are assuming that the heat diffusion is so significant that no heating effects are observed. We can only consider that the effects of the impacts, the aspects that affects rubber friction is just due to Wilk properties, elastic modulus, and power spectral density, which is the surface, the statistical property of the surface roughness. Okay, just check here, I think. Como é que tu quer? Aperta o bano aqui? Não, vou não. Quero ir não. Okay, yeah, this is it. And then this equation, I think I can show quite fast. Here. These are the equations. So, as you can see, the friction coefficient, P is the relative fraction of the contact areas, and G is, what is G? I forgot. What is G? What the fuck? What is G? I forgot. Okay, G is a parameter inside the relative contact friction, which also correlates phi, the angle phi, which is the angle in which the roughness are exposed, the power spectral density. Yep, you see there is CQ, the wave vectors, and also the bulk property of the rubber, again, also in function of the QV cosine phi. Why? Because this is omega, this is frequency, okay? And when I translate frequency to polar coordinates, okay? Okay, good. These are the equations for no temperature cases. Okay. The main point here for tires, actually, the theory usually says takes into the substrate surface roughness components have wave vectors, a minimum and a maximum wave vector. Usually Q defines the wave vector, but Q subscript L, which means length, is the smallest relevant wave vector. So it is the minimum, the lower limit, which usually is the order of magnitude of 2p divided by L. Which, considering tires, L, as I mentioned it, is the tread block, a block of the tread. Okay? And where Q1 can have different origins. And this depends on the conditions which we are analyzing the surface. For example, since QL for tire thread block is smaller than the whole of vector Q0, which is the one corresponding to the nominal condition of the power spectrum of most road surfaces, rubber friction is very insensitive to the exact value of QL. So basically we have QL minus than Q minus than Q1. Okay. Q0 is the wave vector defined by the nominal condition, which is the one related to the normal load, the nominal contact area. And this is called whole of wave vector. Whole of wave vector. Q0 of the power spectra of most road surface, which is very sensitive to QL. Okay, usually QL for tire is lower than Q0. Okay, and then we can assume this condition. Another factor is the Q1, and this is important. This is the large wave vector cutoff, and is related to the minor particles, minor asperities of the road. And the problem is, roads are usually not so clean. So Q1 is related to the road contaminants. Cutoff wave vector. Upper limit. Okay. So, what does it mean? I said that QL is 2P divided by L. So Q1 corresponds to the contaminants on the road. So dust, dirt, sand, brake pads, powder, rubber particles, exhaust particles, exhaust particles. So this kind of stuff. And then when I will build a wave vector related to this, I won't use L. I use 2P divided by D, which D is the diameter of those particles. Okay? So when the tire surface is covered by hard particles of linear size D, the rubber will not be able to penetrate fully on the road asperities. When these asperities have cavities, have valleys in which its size, their sizes, are smaller than D. D size is the wavelength of the surface. Wavelength lambda 1. So it is a short range roughness, definitive for tire friction, and therefore will not contribute to the rubber friction. Okay, So contamination is important. But when I have clean, clean uh, surfaces, when this happens, what really occurs? When this happens, um, the Q1 changes. It is evident. And now the Q1 refers to the tire rubber composition. Because the surface roughness uh, have wavelengths higher than uh, the usual Q1 values. It has wavelengths which are not compatible to be the uh, upper limit of QL, which upper limit of the wave vector, which is the lower QL, the upper Q1. It's incompatible. You cannot assume this. So usually in this case depends on the tire properties. And which one? The amount of carbon black, for example, because carbon blacks and silica, silicium are particles stiff, and if these are close enough to the rubber surface, they will increase, they will have an effect on the surface friction. Okay. So, um, what happens? And this is still valid for without considering Hubble friction, without considering temperature. When we have high local temperatures and high local stresses, which is common, um, it is generated in the thread surface a thin layer, which I also mentioned in the previous video, which is typically of order of a few micrometers. A surface layer of rubber with modified properties, usually named dead layer. It has a minimum contribution to the rubber friction, but it is there. Ciao, buona giornata. Since it is generated because of the stresses of the road causes during the tire use, the thickness of this layer may depend on the type of the road, on the type of the operational conditions. Yeah. Um, and we in this surface can change its layer thickness when the tire goes from one type of surface to another. So it changes depending on the roughness of the asphalt, of the type of the asphalt, and also on the operational conditions. Okay, I think we can write some interesting stuff here. Tire friction. Considering temperature. Okay. Section. Friction. Okay. Rubber friction on hard, rough surfaces mostly depends um, on the oscillations. No, on the hysteretical contributions. Hysteresis contributions to the friction coefficient. These are triggered by the surface asperities, which cause oscillations, on the rubber surface, on the thread rubber surface, because this topic is about tire friction. Thread rubber surface, thus generate an inner weak energy dissipation which hits this process depends on parameters such as velocity, sliding velocity, no, this process mainly depends on parameters such as sliding velocity. Sliding velocity, elastic modulus. I put here the elastic modulus in function of frequency and the power spectral density. The friction coefficient, neglecting the effects from flash temperature, but you do it to more relevant heat diffusion can be described as follows. I'm a poetry. Begin equation. Equation. E... Agora vai. Mi A is equal to 0.5, 1 divided by 2, times the integral of QL the integral in the limits of that wave vectors that I mentioned. So QL at the power of Q at the power no between integral between QL from QL to Q1 at the power. Okay, let's go. The Q at the power of 3 times the power spectral density times the relative fraction of the contact areas times another integral. Species. Another integral from 0 to 2p. Inside this integral, I have the phi, which is the orientations of the roughness asperities. Orientation with respect to what? With respect to the movement direction. The phi cosine phi okay, cosine phi times image of fraction, which is the fraction of the elastic modulus, which I gave in function of the frequency. Okay, but now I will put the frequency in function of the polar coordinates. So Q times velocity times cosine phi. Okay. Divided by 1 minus the Poisson ratio at power of 2. 1 minus which is the Greek letter ni at power of 2 times the nominal pressure sigma 0. Voila, is the equation. Okay. Where PQ begin the equation. P, relative fraction of the contact areas, is equal to Earth of 1 divided by 2 times the square ratio of G. And G is de begin equation de q is equal to 1 divided by 8 times the integral from QL. Não, Mobral. Burro! Que imbecil. Pronto. At power of, oh no, from QL to Q1. Q1. Okay. And inside this integral, I have derivative of Q times Q at power of 3 times power spectral density times integral from 0 to 2p. Of inside this integral, I have the phi, derivative of phi, the angle phi of the asperities. The the absolute okay, the absolute value of, previously I said this as an image, yeah, okay, but now it is only the fraction of the elastic modulus over the 1 minus Poisson ratio at power of 2 times the pressure. E Q V cosine phi close. 1 minus mi square value, close parenthesis, sigma 0. And bar to make it absolute value, and then at the power of 2. So these are the equations which I showed previously. Basically, I'm just writing these equations here. The main point here, the interesting aspect here, when applying Pearson contact model to tires is the wave vector range. Which goes from QL up to Q1. Nice. What time is it? Okay, I will stop here, not because I want, but because I have a lesson, class in the next minutes. Okay, so thank you if you follow me, and have a nice day. See you in the next video.